Greetings. In this video, I'm going to use the PhET Circuit Construction Kit DC Virtual Lab to go over the conceptual difference between resistors in series and resistors in parallel. We'll be gathering a little bit of data, but not doing any significant number crunching. So we'll start this up, and we'll quickly build a circuit. And we'll just have one battery, we'll have a switch. And we're going to put an ammeter in that measures current. All right, and our battery voltage is 9 volts. We'll just leave it at that. And our resistance is 10 ohms. We will leave it at that. So when I close it, and by the way, these blue things represent electrons. Probably figured that. So think about what's going to happen when I close the switch. So I close the switch, and we get a current here of 0.9 amps. I'll open it up again. I always forget when I right-click and when I don't right-click. But just to quickly show you the importance or not of the position of the ammeter, so I'll just add it in a couple different other places. So it reads 0.9 amps. Put it on the other side of the battery. In fact, we'll have it touching the battery, and see what happens. 0.9 amps. So hopefully that convinces you, or at least maybe it doesn't convince you, but it provides you with some evidence that where the ammeter is not, in this case, with one resistor, going to make a difference. I'm not going to obsess here. All right, so we got the 0.9. We can check the voltage. So the voltage across the battery, 9 volts. We learned that. The voltage across the resistor is -9. Notice that I have the leads actually reversed from how I had it on the battery. So we get 9 volts. And -9 just means, like, instead of measuring the waterfall from top to bottom, I measured from bottom to top. So 9 volts across the one resistor. So we just have one, and I probably didn't need both. So series, so the circuit voltage was 9 volts. The current was 0.9 amps. And then when we did the resistor, we got 9 volts and 0.9 amps. And we're going to get the same, probably didn't need that, because one isn't in series or parallel, but that's okay. So now let's just move this over here. And now we're going to add, I should not obsess about looking neat. One more resistor. And just to confirm, this resistor is also 10 ohms. So predict what you think will happen when I close the switch now. Well, how will the current number change? How will the voltage change? Well, look at, I don't even need the switch closed, and the voltage here is 9 volts. So in this case, the current is 0.45 amps. The battery voltage here is 9 volts. Let's check the voltage across each of the resistors. And if I mix these up again, we're going to take the magnitude. So 4.5, and I'll try not to, but if I'm moving them around, 4.5. So in this case, the circuit voltage, so the battery voltage was 9 volts. The voltage for each resistor was 4.5 volts. And the current here is 0.45. So you might say, well, okay, that's there. And when we just had it, we had one resistor, then it didn't seem to matter. But let's just see what happens in this case if we move it. So 0.45. So it seems to not matter where in the circuit, and I didn't move it every possible location. Didn't seem to matter where in the circuit the current is being measured in this type of a circuit. I kind of like it here just because it's a little bit easier to read. When I'm testing a bunch of things, I'm not as concerned about that. Now we'll add one more resistor. Add one more wire. Sorry, it looks kind of crazy. So again, think of what we might see when I close the switch. All right, you've got something in mind. So current, 0.3 amps. Battery voltage still 9 volts. So what do you think will happen with the voltage across each resistor? So 3 volts for this one. Oh, by the way, the resistor I just added is the same value as the other two. So 3 volts for that, and 3 volts for that. So the circuit voltage was 9, and the circuit current, well, here it reads as 3. We won't move it to a bunch of different places, but we'll move it to, let's just move it to between a couple of them. 0.3. I'm not going to move it to all the different places, but hopefully it seems reasonable that throughout the circuit it is the same current here. So the current was 0.3. Oops. I didn't write that down before. So before it was 0.45. I thought I did, but I did not, I guess. 0.45 with 2, and now with 3, it's 0.3. So we still get 3 for each one, and 0.3. So notice for the circuit here, oh, that was not what I wanted to do. The current is the same throughout. And notice for these, the voltage is different, but the sum of the voltage is always going to be 9. So 1 resistor times 9 is 9. 2 resistors, 2 times 4.5 is 9. 3 times 3 volts is 9. So we get some commonality there. Now we're going to move some things apart. So this is our first circuit again, but now we're going to add a resistor in a different way. So the first way that we were adding things together, that is called series. Here we're going to add resistors in a different way. So what do you think will be different about this? How will the current change? Remember, with 1, we get 9 volts, or 9 volts for the battery, and 0.9 amps for the current. So what do you think the current will read, and then what will the voltage read, which we'll test in just a little bit? Oh, so the current is a larger amount here. So 1.8. Let's make a grid here so it's a little bit easier to see these things. Maybe that makes it too busy, I'm not sure. This voltage is still 9. And now let's check the resistor voltage. Oh, 9. And 9, interesting. So here the resistor voltage is 9. So before, when we did this, the current was the same throughout. So let's just kind of do some tests with that. I moved it down here, and that was fine. And try a couple other places. Oh, 0.9 amps. So in this case, the current is not the same every place in the circuit. Let's try the other leg. Remember that the resistors are 10 ohms. And again, it doesn't really matter what they are. And for this, what's important is that they are the same value as each other. And 0.9. Oops. Oh yeah, circuit current. So here, the resistor current was 0.9. Let's add one more. Okay, so let's think about what the circuit current might be. So we went from 0.9 to 1.8 when we added a resistor. Well, one resistor, so we went from 1 to 2. Now we're going to 2 to 3. What do you think will happen? All right, let's test it out. Oh, so now it's 0.9. We got kind of a weird look there. Now it's 0.9 times 3. The battery is still the same voltage. One resistor 0.9. This resistor, I'm sorry, 9 volts. The second resistor is 9 volts. The third resistor is 9 volts. And each resistor is 9. So notice we've got this commonality. So the voltage across each resistor is 9 volts. And here we have 2.7. And think of what the current will be through each leg here. Before, when it was 1, we had 0.9 amps. When it was 2, we had through each resistor 0.9 amps. So let's check this out now. So 0.9. .9, and you can probably guess what the last one will be, but we'll do it anyway, because this is really the last connection and disconnection that we'll make. 0.9. So notice, so for the green highlights, you sum the current through each leg, and it equals the overall current. So let's just take another shade of green here. Actually, I wanted that to be this crazy shade. And now I'll take this to be this shade. And not super different from each other, but not too bad. And then we'll take different shade of yellow. So the green boxes here are showing additive relationships. In the parallel circuit, the current through each leg is the same when we have the same value resistance, but the sum of the currents equals the total current in the circuit. But the voltage across each resistor is the same. With the series circuit, the voltage across each resistor was additive, but the current through each resistor is the same. And if we look at the parallel, which is now kind of crazy and wonky. And by the way, the current meter, also called an ammeter, that is thought to have very small resistance, so basically zero resistance. It's not adding anything, especially in this ideal circuit here. So if we look at the current, so there are three paths for the current to flow through, and so we've got these electrons that are flowing out of the battery. They reach this junction here, and they can go three different ways: through the rightmost resistor, through the centermost resistor, or through the leftmost resistor. And since each of those resistances is the same amount is going to go through each. But there are three paths for the current to flow through. So that means more current is going to flow. Think of that as, and the diagram I'm going to show is from the physics classroom, but I isolated the diagram so we didn't have to watch all these flashing ads. Think of parallel circuit as opening more lanes of traffic, or opening different booths for tolls. There aren't that many toll roads. There are a few toll bridges in Washington State, a few toll rolls, mainly in the eastern part of the United States. But when we open more toll lanes, toll booths, we are going to make traffic flow smoother because here we've got the blue car, the red car, and the truck. With one lane of traffic, they'd each have to stop at the same booth, but here they can flow through different booths. So this makes the flow easier. More trucks are going to flow through a parallel circuit, and that is seen by this right here. We've got more current in the 3 resistor circuit. When we had the resistors in series, they were one right after the other. That's analogous to putting the toll booths one right after the other. Well, you don't need 3 toll booths, but that's going to slow traffic. One toll booth is going to slow traffic some. 3 toll booths right in a row are going to slow traffic down to about a third of the rate. And we see that with the numbers. The resistor current with one resistor, one toll booth. We've got a certain current. We add a second resistor, a second toll booth. The current gets cut in half. We add a third resistor, a third toll booth. The current gets cut to 1/3. So notice when we add resistors, the current through each resistor drops, but the voltage across each resistor stays the same. When we add resistors in parallel, the voltage across each resistor stays the same. The current across each resistor stays the same, but the overall current increases. So think about in which case would the battery wear out sooner. The voltage is the same across the battery in each case, 9s down the columns here. But in this case, when we add resistors, the current gets cut way down. So the battery is going to last a lot longer in the series setup compared to the parallel setup. Parallel setup, if these were light bulbs rather than resistors, we could power more light bulbs this way, and they would all maintain the same brightness. If all the light bulbs in your house were connected in series, they'd all be super dim. But they are in a room, or outlets in a room are wired in parallel. So when you add more outlets, more light bulbs, the brightness does not drop. Add more light bulbs in series and the brightness drops. If you're doing the same thing with outlets, the outlets would not have as much power. I think that's everything I wanted to say. So thank you. This got to be a little bit longer than I planned. So thanks for your patience.